All right, good to go whenever.
Hi, I'm Jeremy Welsh. We were in Dr. Byram Sakharov's lab this summer, and we got to explore some of the cool solid state chemistry that he's doing over there with his team. What he's doing over there is he's funded to explore the chemistry of copper-1. Copper-1 tends to oxidize very readily, and so it takes special care that it needs to be worked with in an inert environment. It likes to turn into copper-2. Turns out that copper-1, when it's made to form a crystal with some organic compounds and some halides, so talking about chlorides or iodide or bromide, then it can do some really cool things in terms of being excited by a certain wavelength of light energy and then emitting another certain wavelength of light energy. What does that all mean? Well, it turns out that thin film laminates are sort of the invisible workhorse of like our day-to-day lives. Just in any LED screen, you're going to see lots of films of these different solid materials that are going to be excited by light, which then can be, or electricity, and can then be turned into light, right? So this is how. And so applying these really thin films of solids like this, which are often, as Sandy mentioned, made out of rare earth elements. We can, another researcher over there is exploring these compounds with lead. So Dr. Sakharov has copper-1. The perovskites have been worked with a lot. They usually involve a metal bonded with a metal and a halide. Okay, so these are the practical applications involve LED lights and scintillators, sensors, things like that. So one of the compounds that I was actually able to, with the help of Poppy, my mentor, synthesize in the laboratory is this guy right here. So we took a solvent, which is TEP, that's triethyl phosphide, and combined it with some copper bromide, and we get this crystal right here, which we believe to be TEP2 copper-1 bromide. And so this is what it looks like under normal light conditions. All right, so one of the things that these materials need to be able to do is be really stable. And one of the things we can look at their stability, one of the ways we can look at their stability, is by doing a test called a PXRD, which is a powdered X-ray diffraction. So we have a crystal here. We wonder what's going to happen if we turn this crystal into a pulverized powder with a mortar and pestle, and are we still going to have the same compound if we pulverize it? This will tell us something about its stability. And so here, this is the powdered XRD test that we get, and this is how we relate to this simulated compound of the crystal. And you notice that the peaks line up really nicely here, and if this were expanded to be bigger, they would fit. And so what this tells us is this compound's pretty stable. We can turn it into a powder, and it's still going to keep that nice crystalline structure that we're looking for. So this here it is under normal light. It's hard to tell under this light much of a difference, but when we put it under UV light, we see some definite green light emitting properties here. So this is a cool sign. And so what does that mean in terms of actual wavelengths being involved? So this is a test that you can do that'll show us the wavelength of light that is that tends to excite this compound. And it tends to be in the UV spectrum, which we just saw, like from the photograph, okay? And when that happens, when it gets actually excited at this 336 about nanometer wavelength, it tends to emit light at about 505 nanometers, which is green. So for a nice little reference here, here's our little visible light spectrum, and see that this is, so, violet here is coming in at 400. We were getting excited about 336, so that would be in the UV light spectrum. It's below 400. And then if it's emitting at about 505, that's going to be right here. So excitation in the UV range and emission in the green light visible spectrum. Let's see. This test. So again, stability, how long are these compounds going to last? They don't tend to be super stable as a rule. So what's going to happen if we cook it to about 400 degrees C for a long period of time? Will it decompose at that point, start to break down, start to turn into something else, or will it remain and go back to a nice little crystalline structure that we want when it does cool down? And this test tells us here that, so we're adding heat here, and we notice that the takeaway message is that when it does actually cool back down, it remains stable. So this would be, actually I believe, a melting point here. So another good promising thing that we see with this guy in terms of stability. This is a test that tells us how well this compound is good at reflecting light. All right, so if we send the light that's sent to it would be, if it's 100%, we're seeing that it reflects back about 77% of that light, which is pretty good, but there are compounds out there that are getting closer to 100 now, in the high 90s. So 77% is pretty promising. But again, they're higher. And then this final test here, it's interesting. So one of the things I learned this summer was a little bit more about, I hadn't necessarily thought a lot about band theory, and which I don't really pretend to understand super well, but what I do know is that it's really useful when it comes to us wanting to explore the outer rims of the universe. I mean, this is what allows, I went to a museum about, I toured a space museum recently, and they were talking about this. Some of these solid state materials, when they become excited, their electrons essentially jump to a higher energy state. And they actually move to these higher orbitals that they wouldn't necessarily possess otherwise. And so when that happens with solids, that can mean strength, and but also it tells us something about excitation here. And so this test actually here does measure the band gap of this compound. So you can see where it's getting excited, and then there's this gap, and then these electrons are actually moving to this higher energy level, which has a lot to do with its photoemission properties in terms of practical uses. They're doing lots of advanced chemistry over there. I'm really grateful to have been a part of it. I don't know that I added a lot to their team, but I certainly learned a lot. And I'd like to thank, obviously, the National Science Foundation, along with all of our faculty members, all of you guys, and all of the people in Byron's lab, including his postdoc, Xing Zhang, Kanika Bashara, Tamana Pinky, and our liaison, Dilruba Poppy. So fine.